Hi. Welcome back to our channel YuvaTeck. Please don't forget to give your feedback after watching this video. We also request you to subscribe our channel and press the bell icon to receive notifications. In the previous video number 7, 8 and 9 we learn about p-n junction formation under unbiased condition. Also we understood the concept of depletion region, and barrier potential. In this video, we will learn about p-n junction diode. A p-n junction forms a popular semiconductor device called p-n junction diode or crystal diode. It is a two-terminal device, namely anode and cathode. Di means two, and it has two electrodes. The word di and, last four alphabet, from electrode gives us the name diode. The P region will act as anode and, N region acts as cathode. The outstanding property of a p-n junction diode is, it will conduct only in one direction. This property helps us to perform rectification operation. The symbol of the diode is shown in figure. The arrowhead in the symbol indicates the conventional current flow direction, under forward biased condition. Let us see the operation of p-n junction diode. Applying external DC voltage to any electronic device is called biasing. As we discussed, there is no current flow in unbiased p-n junction. Under biasing, it allows current flow only in one direction. Biasing is classified as forward biasing and reverse biasing. Let us see the operation of diode under forward biased condition. If the positive terminal of external DC voltage is connected to anode of the diode, and negative terminal is connected to cathode terminal of the device, then this type of biasing is known as forward biasing. If the positive terminal of external DC voltage is connected to cathode of the diode, and negative terminal is connected to anode terminal of the device, then this type of biasing is known as reverse biasing. It is interesting to see that behavior of diode is like a switch. When the diode is forward biased, it behaves like a closed switch and connects the AC supply to the load. However, when the diode is reverse biased, it behaves like an open switch and disconnects the AC supply from the load. Like resistor, the diode does not behave linearly with respect to the applied voltage. They have an exponential current and voltage relationship. We had a discussion on barrier potential concept in the previous video. If a sufficient external voltage, that is, forward bias voltage, is applied to the diode, the free electrons and holes will cross the p-n junction. To achieve this, the external voltage should be more than the barrier potential. Under forward biased condition, the negative terminal of the external voltage pushes free electrons against barrier potential from N region to P region. Similarly, the positive terminal of the external voltage pushes holes against barrier potential from P region to N region. These holes and electrons will cross the p-n junction against the barrier potential. The depletion layer around the p-n junction is decreased under the forward biased condition. If the forward bias voltage is increased at a particular value, the depletion region becomes very much narrow because of the rays in majority carriers cross the junction. These large number of majority carriers constitute a current called forward current. Once the conduction electrons enter the P region, they become valence electrons. Then they move from hole to hole, towards the positive terminal of the battery. The movement of electrons is nothing but movement of holes in opposite direction to that of electrons in the P region. So current in the P region is the movement of holes which are majority carriers. This current is called as hole current. Similarly, current in the N region is the movement of free electrons which are majority carriers. This current is called as electron current. Hence overall forward current is due to majority charge carriers. These majority charge carriers can then travel around the closed circuit and a relatively large current will flow. The direction of flow of electrons is from negative to positive terminal of the external voltage, while the conventional current direction is from positive to negative terminal of the external voltage. Under the influence of applied forward bias voltage, the free electrons get the energy, which is equivalent to the barrier potential, so that they can easily overcome the barrier. While crossing the junction, the electrons give up the amount of energy, equivalent to barrier potential. This loss of energy produces a voltage drop across the p-n junction, which is almost equal to the barrier potential. Please note that the polarities of voltage drop across the p-n junction, in forward biased condition, are opposite to that of barrier potential, but the value is almost equal to barrier potential. In addition to that, there is a small voltage drop across the diode due to internal resistance. The forward voltage drop across the p-n junction is shown in the equation. VF equals V gamma plus IFRF. Here V gamma indicates drop due to barrier potential, and IFRF is drop due to internal resistance. Now we will see the operation of diode under reverse biased condition. Under applied reverse bias condition as shown in figure, holes which form the majority carriers of the P side, move towards the negative terminal of the applied DC voltage, and electrons which form the majority carrier of the N side, are attracted towards the positive terminal of the applied voltage. Hence, the width of the depletion region which is depleted of mobile charge carriers increases. Thus, the electric field produced by applied reverse bias, is in the same direction as the electric field of the potential barrier. Hence, the resultant potential barrier is increased, which prevents the flow of majority carriers in both directions. Therefore, theoretically no current should flow in the external circuit. But in practice, a very small current of the order of a few microamperes flows under reverse bias. Electrons forming covalent bonds of the semiconductor atoms, in the p and n-type regions may absorb sufficient energy from heat and light, to cause breaking of some covalent bonds. Hence, electron-hole pairs are continually produced in both the regions. Under the reverse bias condition, the thermally generated holes in the P region are attracted towards the negative terminal of the applied DC voltage, and the electrons in the N region are attracted towards the positive terminal of the applied DC voltage. Consequently, the minority carriers, that is electrons in the P region and holes in the N region, roam over the junction and flow towards their majority carrier side, giving rise to a small reverse current. This current is known as reverse saturation current. The magnitude of reverse saturation current mainly depends upon junction temperature because the major source of minority carriers is thermally broken covalent bonds. In the next video, we will discuss the reverse breakdown of the diode. Thank you.